When most people think of astronomy, they probably think of planets, stars, and galaxies the way we see them when we look at them in the night sky. It turns out that visible light only shows part of what's happening in our universe. Researchers use X-ray, ultraviolet, gamma ray, and infrared instruments to peer through dust and gas to collect and analyze radiation emitted by objects in our universe. Join us as we discover how the SOFIA science team at NASA Ames Research Center is working with the world's largest airborne telescope to see deeper into our universe than ever before. To tell us more about infrared astronomy, today we'll be meeting with SOFIA project scientist Pam Markham. So Pam, what is infrared astronomy and why is it so important?
Because of its longer wavelengths, infrared light is redder than the reddest color that the human eye can detect. And so astronomers must use special detectors in order to take pictures of astronomical objects at infrared wavelengths. The interesting or useful feature of infrared light is that infrared light is able to pass readily through materials such as dense clouds of gas and dust that would block other forms of radiation, like visible light.
So what types of things do astronomers like to look at?
Things like stars that are much less massive than our own sun, stars that are like the sun but have progressed further along in their evolution. They're nearing the end of their life cycle. Cooled material that has been spewed out by supernova explosions. Planets, comets, shrouds of dust that surround hot, newly formed stars inside that are actually heating up those little dust grains.
Can you give us an example of what something would actually look like in the infrared?
Well, let me show you some pictures of the Orion constellation, specifically the Horsehead Nebula. The visible picture shows some really dark areas, and those are actually dust clouds that are obscuring the visible light that's coming from the stars that lay behind the dust. In the near infrared, you actually see many, many more stars, and in fact, the Horsehead Nebula has practically disappeared. And the reason for that is what you're seeing now is the infrared light going right past all of the dust. So you're actually seeing the stars behind the dust. The mid-infrared has yet a different picture. Same part of the sky, but here you're actually seeing the dust clouds themselves glowing. The dust is warmed at just the right temperature by those stars to glow at just the right wavelength that the mid-infrared detector is actually able to see the dust. And here we see all three images side by side, and you can really see the differences just depending on what wavelength range you look at. And these different ways of looking at the same object really provide a lot of insight to astronomers when they're studying star formation processes.
Is infrared astronomy better than studying visible light?
Well, infrared astronomy is complementary to studies at other wavelengths, including visible light. And each type of investigation at these different wavelengths comes with their own advantages as well as unique scientific insights. It turns out that water, of all things, is an infrared astronomer's worst enemy. Humidity in the Earth's atmosphere absorbs infrared light, making observations at those wavelengths not possible, even from the highest mountaintop. You know, it's kind of ironic to think that an infrared photon may have been traveling through lots of interstellar dust and gas for thousands of years, only to get stopped dead in its tracks once it enters the Earth's atmosphere.
To tell us more about the SOFIA program, we'll be meeting with SOFIA Science Mission and Operations Director, Eric Young. So Eric, what is SOFIA?
SOFIA is the Stratospheric Observatory for Infrared Astronomy. It's a very highly modified Boeing 747 that does observations in the infrared. And to really understand what we have with SOFIA, you have to think about and visualize what had to be done to the airplane to make this observatory. We start off with a Boeing 747, which was one of the largest passenger airplanes in the world. You have to cut a hole in the side of the airplane about the size of a garage door, put in a telescope that's 10 feet in diameter, and then have a control system that will point this telescope and keep it steady to the angle of a dime at a distance of a mile. In order to accomplish that, we've had a large team from a lot of different organizations involved. This included NASA Dryden Flight Research Center, NASA Ames Research Center, and the German Aerospace Center.
What makes SOFIA different from other observatories doing infrared astronomy?
Well, the most obvious thing, of course, is that it's in an airplane, and it's the biggest flying observatory in the world. It is an airplane that flies well above most of the water vapor in the Earth's atmosphere. And water vapor, as Pam mentioned, is the real problem with doing infrared observations because it blocks lots of the spectrum. With SOFIA, there's a huge chunk called the mid and far infrared, which is only visible if you get above the Earth's atmosphere, and that makes it unique. Another unique capability of SOFIA is the ability to fly where the observations have to be made.
Can you give us an example of the kind of science SOFIA is doing?
Well, SOFIA does all kinds of science for astronomy. The observations on SOFIA are open to astronomers all over the world. The very best proposals that are judged by other astronomers to be on SOFIA are the ones that get observed.
We're opening the door.
And so that means that SOFIA does observations from looking at things within our own solar system to nearby stars to stars that are being formed, all the way out to distant galaxies. It's only limited by the innovation and really great imagination of all the astronomers in the world.
To tell us more about the work of the SOFIA science team, we're meeting with NASA Ames Center Director and astronomer Pete Worden. So Pete, as an astronomer, what do you find most exciting about SOFIA?
SOFIA is a state-of-the-art instrument. For the first time, we're going to be able to get high-resolution information in the infrared part of the spectral region. This will revolutionize our understanding of how stars formed, how planets formed, and how the very stuff of life forms.
So who gets to fly on the plane?
The really cool thing about SOFIA is that not only researchers get to fly on it, students get to fly on it, not only graduate students and undergraduates working on this, but teachers get to fly on it. The nice thing about an airplane, which is different from a spacecraft, is that everybody gets to fly on it and gets to work with the instruments. So it gives people not only a chance to interact with the science they're doing in a much more direct way, but it also gives people a chance to feel the excitement of discovery.
SOFIA is conducting a vast amount of science. What do you see as its ultimate goal?
I think the biggest goal is to really begin to understand the early phases of star formation, planetary formation, and the formation of molecules out of which life emerges. You know, the whole field of astrobiology, that how life began, where else is it in the universe, and what its future is tied up in the kind of discoveries that SOFIA will make. So it is a major step forward in understanding who we are and where we came from.
Thanks for joining us, and meet us again on our next Destination Innovation. For more information on NASA's SOFIA program, please visit nasa.gov/SOFIA.